Hello students, welcome to Technogate. In this particular video lecture, I am going to discuss with you people the part number 2 of our unit number 5, that is basics of gantry and plate girders. In our previous video lecture, we had completed about the gantry girders basics. In this particular video lecture, we will study about the plate girders, their basics, their design concepts, every parameters. So my dear students, plate girders is basically, you can say, a complete article. You can say a complete article. So in which we have to discuss various fundamentals. Before discussion of the various fundamentals, diagram of plate girder is necessary. Diagram of plate girders is necessary. So please make the diagram with me. After that we will discuss all the points regarding the plate girders. After that we will discuss all the points. Okay, please make the diagram with me. This diagram is very important for you people, and please make this diagram very clear to you, very clear in your copy. Okay, so let us suppose that this is the introduction. After that we will discuss all the points. Likewise, the plate girders are used when beams are not capable, built up beams are not capable to take the applied load. So we will discuss all the points. Please make the diagram with me. This is our flange plate. Here, flange plate is there. This is our web plate. This is the web plate. Please make the diagram. After that we will discuss all the points. Please be careful. And one point, kindly make the diagram in landscape view, not as the portrait view. Please make the diagram in landscape view, because this diagram, complete diagram is there. Okay. So in this particular case, these are the three plates. This is our 5 mm gap. This is 5 mm gap. I will discuss every point, don't worry. 5 mm gap at top and bottom. This is also 5 mm gap at top and bottom. At top and bottom. Okay. Now these are the flange angles. These are flange angles. Flange angle. This is our web. Okay. Now the bottom flange angle is there. This is our bottom flange angle. This is also the flange angle. Okay. This is filler plate. Here filler plate is there. Red color plate is called as the filler plate. The connection is made using rivets or bolts. Using rivets or bolts, connection is made. Okay. Now this flange from here, which I am marking as dotted lines, this is the tension flange. This is tension flange. This is our compression flange. This is compression flange. This complete value, this is the DW value. Depth of web is only web depth here, not overall depth. Depth of web. This is thickness of a flange, TF flange plate, and this is also the thickness of flange TF. This gap, center line to from here to here, this is width of outstand B shall not be more than 20 times of TF. This is width of outstand in the tension flange, and here this is also width of outstand, but in this particular case B shall not be more than 16 times of TF, or 256 TF by root of Fy, or 256 TF divided by root of Fy, or 256 TF divided by root of Fy. That is the value of width of outstand in compression flange. Width of outstand in compression flange. Let me check anything remains or not. Okay, this is DW, that is okay. 5 mm gap flange plate. These are the flange plates. Flange plate. This is also the flange plate. Flange plate. Now if I am analyzing the situation for the front view, or you can say for the longitudinal view, this is the longitudinal view of this given section. Longitudinal view of the given section. Okay. So my dear students, this is our longitudinal view of the given section. Okay. These are the top and bottom flanges. These are the top and bottom flange. Here flange line is there. This is our line of, this is the line of flange angles. This is the line of flange angles, and the complete diagram looks like this way. The complete diagram looks like this way. The clear distance between the two flange angles is called as D1. This is D1, that is clear depth between flange angles, between flange angles. Here and bearing stiffener is also there. This is the and bearing stiffener. This bearing stiffener is the and bearing stiffener. Black color stiffener is called as and bearing stiffener. This black color is called as and bearing stiffener. And bearing stiffener. Here support reaction will be there. This is our support, in which reaction R1 will be there. Okay. Now at the support, always stiffeners are provided. Always stiffeners are provided. These stiffeners are called as and bearing stiffeners to support or for preventing the buckling of web due to heavy amount of reaction. This is our and bearing stiffener. That's okay. Now if here any heavy concentrated load is there, then the stiffeners are provided are called as the load bearing stiffeners. Then stiffener provided are called as load bearing stiffeners. And similarly, I am writing here B is called as the width of outstand. Width of outstand. Width of outstand. Okay. Now this is the end bearing stiffener. Now these are another horizontal stiffeners, sorry, vertical stiffeners. These are vertical stiffeners. These all are vertical stiffeners. Here, from here, this is our neutral axis. Neutral axis, and this line, red color line, central line is called as longitudinal axis ZZ. Longitudinal axis ZZ. Longitudinal axis ZZ. That is a different diagram. That is a different. This is cross section. This is elevation or front view. Okay. This is ZZ axis. ZZ axis. This is our XX axis. This is our XX axis. Okay. Now these are the vertical stiffeners. These are also the vertical stiffeners. Now some these green pen stiffeners are called as the horizontal stiffeners at neutral axis level. These are called as horizontal stiffeners. We will discuss every point, don't worry. Horizontal stiffeners at neutral axis level. And similarly, these red color stiffeners here, red color stiffeners here are called as the horizontal stiffeners above the neutral axis at a distance of 0.2 d1 from the neutral axis level. These are also called as horizontal stiffeners above or at 0.2 d1 above the neutral axis, or above the basically longitudinal axis, 0.2 d1 above the neutral axis. Let me check if anything remains. Okay, okay, one point is left. After providing all the kinds of stiffeners, let us suppose that these are two dimensions. One dimension is this one and second dimension is this one. Obviously, from these two dimensions, one dimension will be lesser dimension. One dimension will be lesser dimension. That lesser dimension shall not be less than 180 times of TW. And the clear panel dimension, the maximum dimension, shall not be more than, this is our maximum clear, shall not be more than 270 times of TW. This is thickness of web. This dimension is called as thickness of web, TW. So this is maximum clear panel dimension, and this is 180 TW is the minimum clear panel dimension. That's okay. Okay, my dear students, this is the tension flange. Everything we had discussed, everything. Let me check if any value left. Okay, no values left. Okay, so let's discuss all the points very carefully. Please make the diagram very clear. Please make this diagram very clear. Okay, please make this diagram. So let's start the analysis. If I am concluding about the diagram, all the points basically we will discuss, so it's not necessary to conclude all the points here, because now our first point, basically since we are going to discuss only the basics of plate girders, that's why I am writing down all the points number wise, serial number wise. So our first point is there, because all are the basics. Plate girders are used when built-up beams fails to resist the applied load. So plate girders, number point 1 is plate girders are used when built-up beams are not capable to take the applied load, then plate girders are used. One point is left here. From this to this distance is D1, that is shown there. This is our D1 value. That is the clear depth between the flange angles. Okay. Now point number 2. This was the point number 1. Plate girders are used when the built-up sections are not capable, or you can say, since we have designed the beams and there we have learnt about if a single IS rolled section is not capable to take the applied load, then built-up beams are used. If built-up beams fails, then plate girders are used. If plate girders fails, then plate girders with stiffeners are used. If those are also fails, then roof truss girders are used. If roof truss girders are also failed, then we have to redesign the section. However, failure of the plate girders can be prevented using the different kind of the stiffeners, as you see in this particular case. So now we are going to learn where end bearing stiffeners are used, load bearing stiffeners are used, horizontal or vertical stiffeners are used, horizontal stiffeners at the neutral axis level when they are provided, horizontal stiffeners above the neutral axis when they are provided, end bearing stiffeners function, what is the end bearing stiffener function, etc. we are going to discuss. Okay. So my dear students, a plate girder as shown in the figure consists of the tension flange, compression flange and the web. Yes or no? So a plate girder consists of a tension flange, a compression flange and a web. A tension flange, a compression flange and a web. Okay. Now, tension flange consists of flange plate, flange angle and this portion of web, that is called as a web equivalent, or the portion of the web that is sandwiched in between the flange angles. Similarly, the compression flange also consists of the flange plate, flange angles and web equivalent, this web equivalent that is sandwiched, that is embedded in between the flange angles. So number 3rd is compression and tension flanges consists of a flange plate, a flange angle and web equivalent. Tension and compression flanges consists of a flange plate, a flange angle, consists of a flange plate, a flange angle and web equivalent. That is a very, very important point. Web equivalent. Web equivalent. Web equivalent is that portion of web which is embedded, which is sandwiched in between the flange angles. So web equivalent, it is a very, very important note. Web equivalent is that portion of web which is embedded in between the flange angles, in between flange angles. For the tension flange, this web equivalent is equal to, area of web equivalent is equal to 1/8 times of total area of web. Please be careful. And for compression flange, this area, web equivalent area, is equal to, area of web equivalent is equal to 1/6 times of total area of the web. 1/6 times of total area of the web. So if I am writing down, area of web equivalent is equal to, 1/8 times of area of the web for tension flange. Area of web for tension flange, and area of web equivalent is equal to 1/6 times of area of web for compression flange. Why? For compression flange, area embedded is more because compression flange has to take the applied load effectively, whereas in the case of tension flange, rivets are useless in resisting the applied load. Rivets or bolts are useless in resisting the applied load. So if I am concluding, plate girders are generally used when the built-up beams are not capable to take the applied load. The second point, a plate girder consists of generally a tension flange, a compression flange and a web. Tension and compression flanges generally consists of flange plate, flange angle and web equivalent, and web equivalent is 1/8 times of TW for the tension flange and 1/6 times of total area of the web for compression flange. Please note it down very fast. These are the 3 points. Now, fourth point is it is assumed that entire shear force is taken by the web only, and entire ending moment is taken by the compression and tension flanges only. To make sure that the web takes entire shear force, to avoid the direct bearing action in between the flange and the web, 5 mm gap is provided at the top and bottom. So direct bearing action for the load transferring can be avoided. Now, how the load is transferred? That load is transferred through the connections, and the connections to the flange angles, and flange angles, from the flange angles to the flange angles to the, you can say, web. Flange angles to the web. These are the connections basically. Okay. So In general, flange angles are used as unequal angles. Flange angles are used as unequal angles. Longer leg is connected to the flange plate because the entire load has to be transferred through the flange angles, and if longer leg is connected to the flange plate, then load is effectively transferred from the flange plate to the web plate through the connections. So point number 4, it is assumed that entire shear force is taken by, it is assumed that entire shear force is taken by web only, is taken by web only. Entire shear force is taken by web only, and entire bending moment is taken by flanges only, is taken by flanges only, Point number 5, to make sure that web only takes the shear force, a 5 mm gap is maintained between flange plate and the web plate to avoid the direct bearing action between them. To make sure that web only takes the shear force, web only takes shear force, 5 mm gap is maintained, 5 mm gap is maintained between flange plate and web plate to avoid the direct action between them. Web plate to avoid direct bearing action between them. To avoid direct bearing action in between them. Okay. Now it means load is transferred from the flange plate to the flange angles and to the web plate through the connections only. Or you can say, it means load is transferred from flange plate to the web plate through the flange angles and the connections only, and their connections. That is it means load is transferred from flanges to web using flange angles and their connections. Using flange angles and their connections. Using flange angles and their connections. Point number 6. Unequal angle sections are generally preferred and longer leg is connected to the flange plate of the flanges. To get more bearing area. So, unequal angles are generally used as flange angles. And longer leg is connected to the flange plate, to get more bearing area, more bearing area, to get more bearing area. So these are another 3 points. These are another 3 points. It is assumed that entire shear force is taken by web only and the entire bending moment is taken by flanges only. To make sure that web takes only the shear force, a 5 mm gap is maintained in between the flange plate and the web plate, and hence load is transferred without bearing action, without direct bearing action, from the flanges to the web through the flange angles and the connections. Unequal angles are generally used as the flange angles, and longer leg is connected to the flange plate to get more bearing area or more transferred area, to get the more area for transferring the load. More area for transferring the load. More area for transferring the load. Please note it down very fast. After that we will discuss more points. After that we will discuss more points. Please note it down very fast. Okay. Now, width of outstand in compression zone is 16 TF or 256 TF by root of Fy, and the width of outstand in tension zone is basically so point number 7. If I am talking about the width of outstand, that is 20 TF, width of outstand in compression zone shall not be more than 16 times of TF, shall not be more than 256 TF divided by root of Fy. Root of Fy, the point number 1. Point number 2 is width of outstand in tension flange. Width of outstand in tension flange or tension zone or tension zone shall not be more than 20 times of the TF. Very, very important values. Point number 8. For resisting the shear, depth of web is only the depth of web, not the overall depth as in the case of the beams, because here in the web and flange plate there is some gap. That's why only depth of the web is considered as the depth of the web, not the overall depth as was in the case of the beams. So for resisting the shear, depth of web is taken equal to depth of web only, not the overall depth. For resisting the shear, depth of web is taken as dw only, depth of web only. In bracket I am also writing not the overall depth, not the overall depth. Please be careful. So my dear students, if I calculate the value of tau VA, that is equal to the maximum shear force divided by area. Maximum shear force is V, area is dW into TW, dW into TW, that value shall be less than or equal to 0.4 Fy in working stress method and 0.52 Fy, 0.4 Fy in working stress method shall be less than or equal to 0.52 Fy in limit state method. In limit state method, that is tau VA. That is tau VA. For resisting the shear, Depth of web is taken only the depth of the web. Please be careful, not the overall depth. Not the overall depth. Okay. Now point number 9. Very important point is there from exam point of view. Point number 9 is very important depth. The economical depth of the plate girder. Economical depth means which corresponds to minimum weight. If weight is minimum, obviously cost will be minimum. The economical depth of plate girder. Economical depth of plate girder is given by what is the economical depth? Overall depth. I am talking about the overall depth. Please be careful. Economical depth corresponds to minimum weight. Corresponding to minimum weight, because if weight is minimum, automatically cost will be minimum. Economical depth, that is D economical, is equal to 1.1 times of whole under root of M maximum divided by sigma BC into TW. Sigma BC into TW. Sigma BC into TW, that is the economical depth. Economical depth of plate girder. Economical depth of plate girder 1.1 times of M maximum divided by sigma BC into TW. So if I am concluding up to here, width of outstand in compression zone, width of outstand in tension zone. For resisting the shear, only the depth of web is taken as the dW only, and that is equal to dW, and calculated using V divided by dW into TW, that shall be less than or equal to 0.4 Fy or 0.52 Fy. That depends upon working stress and limit states method. Width of outstand in tension zone shall be economical depth of plate girder, that corresponds to minimum weight, not the minimum cost, because minimum weight automatically corresponds to the minimum weight. That is equal to D economic 1.1 times of M maximum divided by sigma BC into TW whole under root. Okay, whole under root. Okay, now please note it down very fast. After that we will discuss remaining points. Total approximately 30 points are there. Total approximately 30 points are there. Please be careful. Okay. Now self weight of the plate girder. Now self weight of plate girder. Self weight of plate girder. Point number, whatever the point number is there, I think 9, 3, 7, 7, 8, 9, 10. 10th point is there. Self weight of plate girder is equal to the superimposed load divided by 302. Superimposed load divided by 400. So self weight of plate girder is taken equal to self weight of plate girder is equal to W self, that is equal to W by 302 W by 400. W by 302 W by 400. W is equal to total live load or superimposed load. Total live load or superimposed load on the plate girder. This is the self weight of plate girder. How it is calculated? We have the simple formula. This will be given to you. Total live load or superimposed load. Now the permissible bending compressive stress, since there are no chances of the buckling, due to which because we have applied all the kinds of the stiffeners. So permissible bending compressive stress, that is sigma BC is equal to 0.66 Fy or 0.66 FCB Fy whole divided by FCB to the power n plus Fy to the power n whole to the power 1 by n. 0.66 Fy or 0.66 FCB Fy whole divided by FCB to the power n plus Fy to the power n whole to the power 1 by n, whichever is less in working stress method. FCB was given by the same formula, K1 into x plus K2y whole multiplied by C2y C1, that we had discussed in our beam chapter. N is called as an imperfection factor. N is called as imperfection factor, and its value is fixed, that is 1.40. This formula is called as Rankine-Merchant formula. This formula is called as Rankine-Merchant formula. However, sigma BC in limit states method is also given by the formula Fy by 1 whole divided by phi plus whole under root of phi minus lambda square. That is the limit states method. Sigma BC in a limit states method is equal to Fy by 1.1 whole divided by phi plus whole under root of phi square minus lambda square in a limit states method, whereas lambda is the non-dimensional slenderness ratio FCB divided by Fy. This was the formula given by Perry-Robertson. So this formula is Perry-Robertson formula. This formula is Perry-Robertson formula sigma BC. Okay. Now if I am concluding up to here, self-weight of plate girder is given by W by 300 to W by 400, whereas W is the total load, live load or total superimposed load. Permissible bending compressive stress is given either by the Rankine-Merchant formula or by the simple formula in working stress method or by Perry-Robertson formula in the limit states method. Please note it down very fast. After that we will discuss the remaining points. Please note it down very fast. Okay, so let's discuss more points. Now point number 12. Okay. Now most important points starts. The point number 12 is, if D1 by TW is less than 85 or less than or equal to 85 basically, if D1 divided by TW is less than 85, no stiffener is required. There are no chances of buckling. D1 value is very less, no chance of buckling. As D1 increases, D1 by TW increases. So there may be chances of buckling and hence stiffeners will be required. So if D1 by TW is less than or equal to 85, there is no possibility of buckling of the web. There is no possibility of buckling of web, and hence no stiffeners are required, and hence no stiffeners are required. there are no stiffeners are required. Now if d1 by tw is more than 85, next case is if d1 by tw is more than 85, then buckling due to excessive amount of shear force may be there, and hence vertical stiffeners are provided to resist the excessive amount of shear force. So if d1 by tw is more than 85, there are chances of buckling. There are chances of buckling due to more amount of shear force, due to more value of shear force, and vertical stiffeners are provided to prevent the buckling of web, and vertical stiffeners are provided to prevent buckling of web, to prevent buckling of web. Okay, to prevent the buckling of web. That's okay. Now 14th point, if d1 by tw is more than 200, d1 by tw is more than 200, then horizontal stiffeners above the neutral axis at a distance of 0.2 d1 are provided. Horizontal stiffeners are provided. If d1 by tw is more than 200, there are also the chances of buckling of the web due to excessive amount of the shear force, and hence horizontal stiffeners are provided above the neutral axis, above the neutral axis at a distance of 0.2 d1, at a distance of 0.2 times of d1 from neutral axis, d1 from neutral axis, d1 from neutral axis. What are the function of these horizontal stiffeners? They prevent the web buckling due to more amount of the bending stresses, bending moment and bending stresses. So they prevents web buckling due to more value of bending moment, due to more value of bending moment. These horizontal stiffeners prevents the buckling of web due to more amount of bending moment. Another case is also left likewise, d1 by tw is more than 250, d1 by tw is more than 400. That case is also left. So if I am concluding, if d1 by tw is less than 85, no possibility of buckling of web, no stiffeners required. d1 by tw more than 85, chances of buckling due to more shear force, and vertical stiffeners are provided. d1 by tw more than 200, chances of buckling due to more value of bending moment, and hence horizontal stiffeners above the neutral axis are provided at a distance of 0.2 d1 above the neutral axis. Please note it down very fast. Please note it down very fast. Okay. Now, point number 15. If d1 by tw is more than 250, then horizontal stiffeners are provided at neutral axis level, which prevents the buckling of web due to more shear force in between the vertical stiffeners. So point number 15, if d1 by tw is more than 250, then these horizontal stiffeners at neutral axis level are provided, which prevents the buckling of web in between the vertical stiffeners. So horizontal stiffeners at neutral axis level are provided which prevents the buckling of web in between the vertical stiffeners. In between the vertical stiffeners, and the question arises in your mind is that when the in between the vertical stiffeners web buckling happens, that is due to excessive amount of shear force in between the vertical stiffeners due to very much value of shear force, This is the criteria. If d1 by tw is more than 250, horizontal stiffeners at neutral axis level are provided, which prevents the buckling of web in between the vertical stiffeners, due to heavy amount of the shear force. Now the last point is, if d1 by tw is more than 400, then sections must be redesigned. If d1 by tw is more than 400, then section must be redesigned. Then we have to go for either redesigning the section, or we have to use roof truss girders, Point number 17. At the level of the support, to resist the effect of the reaction, end bearing stiffeners are provided. Due to support reaction. At the support level, to prevent buckling, this is our support. At support level, to prevent the buckling, of web, and here one point is also there, due to reaction, this flange may also buckle. This flange may also bend by mistake. Due to transverse loading, bending is there. So to prevent the buckling of web and bending of flange, at support level, to prevent the buckling of web and bending of flange, end bearing stiffeners are provided. Due to support reaction, for support reaction, for resisting the effect of support reaction R. Okay. Now what is the value of support reaction? That is equal to V maximum shear force. Okay. So if I am concluding about these 3 points, if d1 by tw more than 250, then we have to provide the horizontal stiffeners at neutral axis level, which prevents the buckling of web due to more value of the shear force in between the vertical stiffeners. If d1 by tw more than 400, sections must be redesigned. At support level to prevent the buckling of web and bending of the flange, the end bearing stiffeners are provided. Under the concentrated load to prevent the buckling of web, and load bearing stiffeners are provided that are also the you can say part of that are also the part of or you can say type of a vertical stiffener. Please note it down very fast. Please note it down very fast. Okay. So under the concentrated load, vertical stiffeners are provided called as load bearing stiffeners due to excessive amount of the bearing stresses due to concentrated load. Point number 18, under concentrated loads due to excessive amount of bearing stresses due to excessive amount of bearing stresses due to excessive amount of bearing stresses, vertical stiffeners provided are called as vertical stiffeners provided are called as load bearing stiffeners. Vertical stiffeners provided are called as load bearing stiffeners under the concentrated loads because due to the concentrated loads, heavy amount of the bearing stresses are developed at the contact surface of the flange and the web plate. Likewise at this location. Likewise at this and this location. So to resist that bearing stresses, the load bearing stiffeners are provided. Now next point. After providing all the types of the stiffeners, the maximum clear panel dimension shall not be more than 270 TW and minimum clear panel dimension shall not be less than 180 TW. So very important point is also there. After providing all the stiffeners, the maximum clear panel dimension shall not be more than 270 TW and the minimum clear panel dimension shall not be less than 180 times of TW. 180 times of TW as shown in the figure. Okay. Now, since these end bearing stiffeners are just above the reaction at outside of the beam section or plate girder section, that's why they must be designed as a column. They must be designed as a column. That is, they should be perfectly vertical, purely vertical. They should not be joggled. Joggled means they should not touch the web plate. In the cross section you can see end bearing stiffener, web plate. There is a gap in between the end bearing stiffener and the web plate. Otherwise, if they are joggled, if they are not perfectly vertical, then their load, or due to these stiffeners, if load comes on these stiffeners, then load may go to the web and web may buckle. So they must be perfectly vertical. They should not touch to bend the web plate. And to make sure that they should be purely vertical, or you can say they should not be joggled, a packing plate or filler plate is used. A packing plate or filler plate is used. A packing plate or filler plate is used. Okay. So please note it down these 2 points. If I am concluding, under the concentrated loads Due to excessive amount of bearing stresses, vertical stiffeners are provided, and after providing all the stiffeners, minimum clear panel dimensions and maximum clear panel dimensions should be 180 TW and 270 TW. Okay. End bearing stiffeners, these are designed as a columns. Point number next 19 point number is there. End bearing stiffeners are designed as columns. Are designed as columns. That is, they should be purely vertical. That is, they should be purely vertical. They should be purely vertical. And they should not be joggled. And they should not be joggled. They should not be joggled. That is, they should not touch. They should not be bent to touch the web plate. They should not be bent. They should not be bent to touch the web plate. To touch the web plate. So, end bearing stiffeners are designed as columns. They should be purely vertical. However, these load bearing vertical stiffeners should not be designed as a columns. They can be joggled, but end bearing stiffeners cannot be joggled. They should not touch the web plate, or they should not be bent to touch the web plate. So the gap between the web plate and the end bearing stiffener is maintained by providing filler plate or packing plate. Note number 20 or point number 20. Gap between web plate and end bearing stiffener. Web plate and end bearing stiffener. Web plate and end bearing stiffener. End bearing stiffener should be maintained by providing. Should be maintained by providing the filler plate or the packing plate. By providing filler plate or packing plate or packing plate. Gap between the web plate and end bearing stiffness should be maintained by providing the filler plate or the packing plate. Okay, filler plate or packing plate. Now, purpose of a filler plate is just only to fill the gap. It does not take any kind of the structural load. Purpose of filler plate is just only to fill the gap. Is just only to fill the gap. It does not take any kind of structural load, and it doesn't takes any structural load. So the gap between the web plate and the filler plate, end bearing stiffness should be maintained by providing the filler plate or the packing plate. The purpose of packing or the filler plate is just only to fill the gap, and it does not take any kind of the structural load. It does not take any kind of the structural load. Okay, please note it down these points very fast. Please note it down. If I am concluding about end bearing stiffener, they are designed as columns. They should not be joggled. Gap between the end bearing plates and the bearing stiffener and the web plates should be maintained by filler plates. Please note it down very fast. Now, the vertical stiffeners that are in front of you, these stiffeners, these may be vertical, these may be vertical, these may be vertical, are not designed as columns, and hence they can be joggled. They can be bent to touch the web plate. They can be bent to touch the web plate. They can be bent to touch the web plate. Okay. So, point number 22 or 21, whatever the point may be. The vertical stiffeners, are not designed as columns, are not designed as columns. Vertical stiffeners are not designed as columns. They should be bent, means they can be joggled, and hence they can be joggled. That is, they can be bent to touch the web plate. That is, they can bent to touch the web plate. To touch the web plate. Okay. Now, our next point number 23. If only stiffeners are only the means for providing the torsional restraints, because stiffeners are used for torsional restraints basically, not as a warping restraints. So, moment of inertia of the stiffeners should not be more than d cube t divided by 250 into r divided by h1, r divided by w or r divided by h1. That is important things. Okay. Now, please note it down, this formula. Now, this point. The vertical stiffeners are not designed as columns, and hence they can be joggled, that is, they can be bent to touch the web plate. Now, point number 23. Point number 23. If stiffeners are only the means, if stiffeners are only the means of providing torsional restraints, if stiffeners are only the means of providing the torsional restraints, moment of inertia of the stiffener, that is I value of stiffener shall not be more than d cube t divided by 250 into r divided by capital W. R divided by capital W. That is a very, very important fundamental. Whereas d is the overall depth. Capital D is the overall depth. Capital D is overall depth. T is the total thickness of compression flange from here to the distance where the flange angle finishes. T is the total thickness of compression as well as the tension flange. T is the total thickness of compression flange. R is the maximum support reaction and W is the total superimposed load that we had discussed. Okay. If the stiffeners are only the means of providing the torsional restraints, then Means torsional strengths are not provided by here the flange cleat or the web cleat, or the beam can be casted into a wall, girder can be casted into a external wall. Above against those points, if only the stiffeners are only the means, then moment of inertia shall not be more than this value, d cube t divided by 250 into r by w. Okay. Now point number 24, the minimum spacing of the vertical stiffeners, this is stiffener to this is stiffener, minimum spacing, center to center spacing should be 0.33 d1, and the maximum spacing is 1.5 times of d1. d1 is the clear depth of the flange angles. So the minimum spacing of vertical stiffeners is equal to 0.33 d1, and maximum spacing of vertical stiffeners is equal to 1.5 d1. Maximum spacing is 1.5 d1 and minimum spacing is 0.33 d1. So if I am concluding, if stiffeners are only the means of providing the torsional strengths, however torsional strengths can also be provided by using flange cleat, web cleat, or the beam can be, or the girder can be casted into a external wall, then moment of inertia of the stiffeners, moment of inertia of the torsional strengths shall not be more than d cube t by 250 into r by w, whereas symbols has their usual meanings. Minimum spacing of the vertical stiffeners is equal to 0.33 d1 and the maximum spacing of vertical stiffeners is equal to 1.5 d1. Please note it down very fast. After that we will discuss something more about plate girders. Please note it down very fast. Now point number 25. Since end bearing stiffeners are designed as a columns, so if you have remind about the design of columns, imaginary columns, or to prevent the diagonal buckling, web is treated as an imaginary column. Here also the same thing is there. So for end bearing stiffeners, the imaginary column or web is treated as an imaginary column. Point number 25, for end bearing stiffeners, web plate is treated as imaginary column whose length is equal to, that is d1, if I am talking about d1, whose length is taken equal to 40 times of tw, whose length is 40 tw. That is a very important point. Please be careful. For end bearing stiffeners, since end bearing stiffeners are designed as the, you can say, the columns, so the web must be treated as a fixed column with both ends fixed, whose length is this one. So effective length will be 0.7 times of d1, because total length is d1. So effective length will be 0.7 times of d1. So L effective of imaginary column is equal to 0.7 times of d1. Both ends are fixed. So approximately value will be 0.5 L or 0.65 L. We have assumed it 0.7 times of d1. 0.7 times of d1. Okay. Now please write down the problem with me. This completes your plate girders. Please write down the problem with me. After that we will discuss their solutions. Okay. If I am concluding about this point, end bearing stiffeners are designed as the columns, and hence web must be treated as an imaginary column whose length is 40 tw and effective length whose basically, this is basically height or depth. Effective length is 0.7 times of d1. Please note it down very fast and write down a problem. write down a problem. We will discuss three problems for plate girders. We will discuss three problems for plate girders that are very, very important. That are very, very important. Okay. At a section along the span of a welded plate girder, question is, at a section along the span of a welded plate girder, along the span of a welded plate girder, where web is spliced, bending moment is M, bending moment is capital M, bending moment is capital M. Okay. At a section along the span of a welded plate girder, where web is spliced, bending moment is M. If girder has top flange, web and bottom flange, if we have to make the diagram itself by ourselves, because diagram is not given in the problem. So if girder has top flange, comma, web and bottom flange, of equal area, calculate the bending moment which is shared by, calculate share of bending moment M, which would be taken by spliced plate. Calculate the share of bending moment which would be taken by a spliced plate. Very, very important question is there. Which would be taken by spliced plate. Very, very important problem is there. Very, very important problem is there. Please note down the problem. After that, we will discuss its solution. Okay. So, my dear students, kindly have a look on the problem. Girder has top flange, web and bottom flange. Top flange, let us suppose that this is having the dimensions of B and T. Okay. Now web, let us suppose this is also having the dimensions of B and T. And the bottom flange, also, which is having the dimensions of B and T, of equal area. So this is our neutral axis level. Okay. Now, since we have to consider T square, T cube, T by 2 are neglected, so take the flange area as a line area. take flange area as line area. It means t square, t cube, t by 2 are assumed to be neglected. Now if I make the diagram in the front view where it or how it looks, let us suppose that this is the top flange, this is the bottom flange, and the bottom flange. This is the top flange, this is the bottom flange. Okay, top flange and bottom flange. Okay, now at a section along the span of a welded plate girder, means here plate web is welded, spliced, and at this particular location, this is our web splice. Obviously this will be welded to the plate girder, likewise this, using the bolts, and here this is our welding portion. Here this is our welding portion. Okay, now this is welded, so moment taken by this web splice will also be equal to moment taken by the web, because web splice transfers the moment to the web, So we can say that moment taken by web splice must be equal to moment taken by the web, moment taken by web. Here the bending moment, web splice location, the bending moment is capital M. It means moment taken by the web is in the proportion of MW by IW, that must be equal to moment taken by web, that is given as M. So M divided by I. We have to calculate the value of bending moment which would be taken by the spliced plate, means we have to calculate the value of MW. Here symbols has their usual meanings. MW is the moment taken by web. Capital M is the total moments here. Capital M is total moment. Capital I is, you can say, moment of inertia, total moment of inertia about neutral axis, and IW is equal to moment of inertia of the only web portion. Moment of inertia of a only web portion. Okay. Now we have to calculate initially the total moment of inertia I. I is equal to, because two flanges are having their separate neutral axis, let's suppose that XX. So parallel axis theorem will be applied. For these cases. So my dear students, I will be equal to this dimension as it is opposite cube by 12. This is for web portion, TB cube divided by 12, that's okay. This is our web portion, plus two flanges are there. For one flange, this dimension as it is opposite cube by 12, that is neglected. IXX being neglected value, because it gives me the value B into T cube by 12, and t square t cube are being neglected, plus area is b into t into y square. Y square will be b by 2. T by 2 will be neglected. B by 2 whole square. B by 2 whole square. TB cube by 12. 2 times of b cube t divided by 2. B cube t divided by 2. This is 0. So after calculation, this is 2 flanges. These are 2 flanges. So after calculation, I found the value 7 TB cube by 12. 7 TB cube by 12. I is okay. Now moment is given. Now IW, moment of inertia of only web, that is TB cube by 12. IW is only TB cube by 12. T as it is, opposite cube by 12, that's okay. MW we have to calculate. We can calculate. Okay, let's calculate. MW is equal to capital M divided by capital I, that is 7 TB cube by 12. 7 TB cube above multiplied by 12 whole multiplied by IW multiplied by IW is TB cube by 12. IW is TB cube divided by 12. 12 to 12 cancelled out. TB cube to TB cube cancelled out. So moment taken by the web is equal to total moment divided by 7. Moment taken by web is equal to total moment divided by 7. Very, very important fundamental. Very, very important question, gate problem. Okay. So here in this problem, moment taken by the web was given. Now we have to calculate the how much amount of the load, amount of bending moment has to be taken by the spliced web plate. Spliced web plate, from equilibrium conditions, moment taken by web splice must be equal to moment taken by the web. This is not having the meaning m is equal to m. No, no, no. This is the equilibrium condition. This is the equilibrium condition. M by I, sigma by y, E by R. You can equate using flexural formula. So moment and moment of inertia are only in this particular relationship. So you can equate, and you have found the value. We have found the value. M moment taken by the web is equal to m by 7. Please note it down very fast. After that we will discuss another numerical. We will discuss another question. Please note it down very fast. Okay. Okay. Now next question. That is the next question for plate girders. Okay. Kindly write down the question with me. After that we will discuss its solution. Question is, a symmetrical plate girder has been fabricated using 3 equal plates. Means approximately the same question is there. A symmetrical plate girder has been fabricated using 3 equal plates. Using 3 equal plates. If a circular hole of diameter equal to, if a circular hole of diameter equals to half of its height, equals to half of its height is centrally cut in the web, is centrally cut in web, then what is the approximate ratio of, then what is approximate ratio, what is approximate ratio of strength of, approximate ratio of strength of punctured girder, punctured plate girder, and to that of original plate girder, original plate girder. Means, my dear students, this is the same question as we had discussed just 10 minutes before. So if I am talking about the solution, what is the problem? Symmetrical plate girder has been fabricated using 3 plates. This is our one plate having B into T, B into T, and here also this value is B into T. Now, a circular hole of diameter equal to half of its height, this height is half value, that is B by 2, is centrally cut in the web. Means the diagram looks like this way. The diagram looks like this way. Okay, and here the hole is centrally cut, in the web. This is having the diameter equals to B by 2, half of its height. Then what is the approximate ratio of the strength of the punctured girder? In general, my dear students, if I am talking about the strength means basically the flexural strength. And flexural strength, as we know, that is called as the section modulus. Flexural strength, or you can say the bending strength, is called as the section modulus, that is equal to I by Y maximum, I divided by Y maximum. So, my dear students, if I am talking about the Y maximum, that is the neutral axis level for both the cases, for the above case and for the below this case also, this is our Y maximum, and this is also Y maximum. Since Y maximum is same for both the cases, since Y maximum is same for both cases, that's why our Z is directly proportional to I value. That's why only compare value of moment of inertia to compare their strengths, Okay, means this is our second part, I2, and that was our first part. I2, that is moment of inertia of punctured girder, punctured plate girder, and I1 moment of inertia of the original plate girder that we had discussed just in previous problem, and I1 that is moment of inertia for the original plate girder before puncturing, before making the hole, before making the central hole. Okay, so I1 moment of inertia of original plate girder, original plate girder was equal to, our answer was 7 TB cube by 12, 7 TB cube divided by 12 we had discussed. Okay, so I2 is equal to moment of inertia of the punctured girder, that is the important thing. From the total value, let's deduct the moment of inertia of this central hole. Okay, that's okay. So from total value, that is 7 TB cube by 12 minus this central hole. From the web, this is this dimension as it is, this dimension cube by 12 means b by 2 whole cube by 12, that is this location, our value will be there, and after calculation I found the value is equal to 55 by 96 TB cube. That's okay. Moment of inertia of the punctured girder. I had done just only one thing. From the original value, I had deduct this portion moment of inertia. This portion moment of inertia is this as it is, t as it is, b by 2 cube divided by 12, TB cube by 12. Okay, so I1 by I2 we have to calculate. That is our answer. So I2 is equal to 55 by 96 TB cube whole divided by 7 by 12 TB cube. So 12 by 7 TB cube. TB cube to TB can cancelled out. 12 8 ja 96. So 55 by 56. That is 55 by 56. If I compare this value in the percentage multiplied by 100, that is 98% answer. Means strength of punctured girder is 98% of the strength of original girder. Very important problem. So in this particular problem, we had discussed a symmetrical plate girder was there, in which original I1 was this one, punctured I2 was this one. We have to calculate the ratio of I2 and I1 because Y maximum is same for both the cases, either for punctured case or without punctured case or original case. Please note it down this one. After that we will discuss another problem. Please note it down this one. After that we will discuss another problem. Very important question was there. So my dear students, in this particular video lecture we had discussed about the basics of plate girders along with their numericals. In the next upcoming video lecture, we will start our new unit, that is unit number 6, that is industrial roofs, along with design of the purlins, angle purlins and channel purlins. We will discuss in the next upcoming video lecture. And our unit number 7, that is very important for you people, that is plastic analysis of beams and frames, in which we will discuss about the plastic moment capacity, the collapse load conditions, the upper bound theorem, lower bound theorem, principle of virtual work or imaginary work, according to which external work done must be equal to the internal work done, assumptions in the plastic analysis, and various cases, likewise the simply supported case, propped cantilever case and the cantilever beams case. What is the gable mechanism, what is the sway mechanism, that we will discuss in our plastic moments of beams and frames, and along with our syllabus will be completed. So from the next upcoming video lecture we will start our industrial roofs, and we will also start from the followed by plastic analysis of beams and frames. Thank you so much. Goodbye and keep learning with TechnoGate. Thank you.